Hello everyone, and welcome to today's Popular Science lecture in the library with Andreas Archenti. But before I hand over to Andreas, I'd like to say a few things. First of all, in case of an emergency, there are two emergency exits, one over there and one over there. And also, as you can see, this lecture is being filmed, and it's going to be posted on YouTube and on our website. So if you're uncomfortable being on film, please just refrain to the back or to the sides. And you are, of course, welcome to ask questions, but please wait until the end of the lecture. Then I can hand this box around, which is also a microphone, and that way your questions will be recorded as well as the answers. So now I'd like to welcome Andreas Archenti, who's here to talk about precision engineering. Welcome.
Thank you so much for the kind introduction. Thank you also for having me here for this short talk. Yes, my name is Andreas Archenti. I work here at KTHB as a professor in this subject and doing research on precision and dependability. The subtitle, "And the machine that makes other machines," is something I added because that's basically a typical application we see of precision engineering in today's society. First, I would like to ask you, how could Michelangelo do this figure, or this statue? The statue of David, it can be seen in Florence. When he made it around 500 years ago, he had poor volumetric accuracy and low stiffness. And that's things that we today consider granted when we do precision things. And as you see, the figure is quite impressive. It's around 5 meters tall and has small features around 1.5 millimeters. So the dynamic range is 20,000 to 1, and he could do this 500 years ago. So the question is, how could he do it? And I will answer it at the end of this presentation. Maybe some of you come up with the answer as well, because it's embedded in the presentation today. One example on modern machinery that creates things are industrial robots or manipulators. And as you see here, the machine is forming a piece of metal with, it could be additive manufacturing, but it could also be subtractive manufacturing of things. And as you see, it shapes it. And that's a typical application we see today, is where part of the things that I will present will be considered. So I will have a short introduction, historic overview. Then I will talk about design and manufacturing of products, and especially machines that make other machines, because that's the key issue here. Then I will also talk a bit about the contribution of precision to the revision of the SI unit system that I think most of you are familiar to. And then I will summarize it at the end and give us some outlook of how I see on the future. The presentation is designed in that way that it's more kind of luring you guys into the subject, because we need a lot of new young people coming into the precision engineering field. So I have tried to have a kind of smorgasbord of different application areas, not particularly only my own research, but I have also example of that in here. So the idea is to look at machinery as fingerprints, how we can measure and characterize the fingerprint of machinery. As you will see, that will be a very crucial part of precision engineering subject and metrology. So, introduction and historic overview. First, we start with the definition. Boring, we need some text here as well. So precision engineering is, first of all, a multidisciplinary scientific area. That means that you cannot only have one domain knowledge to be successful in precision. You need to have a lot of different knowledge. From mechanical engineering to ultra-precision machining of components through metrology and optical design, for instance. So you really need to be working over the different subject area and the different domains. Discipline encompassing the design, development, measurement, and of high accuracy components. So that's one of the drivers today, if we define it. And a sub-topic of precision is precision manufacturing. And I'll also give you some example at the end, how precision manufacturing has also revolutionized how we see on our surrounding today as human beings, and so on. So if you look at drivers for precision through history, we can go further back. We saw an example of Michelangelo earlier and Leonardo da Vinci, those Renaissance genius that developed a lot of nice things already done. But if we start from the 16th or let's say 17th century, we see, especially in astronomy, with the fundamental sciences, drive to our need or our willing to understand our surroundings and so on. So there we had to embed a lot of those philosophies about precision. Also looking at wind and water mills, for instance in the Netherlands, where you pumped water and made land livable where you can live on. It started much earlier, but it was very perfection at that time. And going towards to where we are today, where we see a lot of sustainability issues, lower friction in machinery to have less fuel consumption and so on, as really high motivators for developing the field of precision and the different domain knowledges. One important step was to mass production, and it was this gentleman that introduced it, Henry Ford. He wanted to produce cars for everyone, that everyone could afford and buy them. And what he understood was he needed to have good components for interchangeability. So that means that he needed a standard to make components so you can change them with each other if you need to replace them. And one of the enablers, or the enabler of that, was actually a Swedish guy, Carl-Evert Johansson, C. Johansson. He invented the gauge blocks, as you see there in the box. And with using of those gauge blocks, I have one of those boxes here actually, you could combine different parts, steel parts, precision manufacturers together, and by that making reference dimensions that you can calibrate other instruments against. So for instance, here we have 2 dimensions, and they are so precise manufactured so you can put them together like these steel parts. So you get atomic bindings together with them. And this was one of the, I think, the greatest invention ever in the field of precision, because that enabled actually Ford to mass produce cars that had interchangeable parts. And that really revolutionized the whole industry in that time. Continuing a bit, so we have said now the need for manufacturing of parts, components was a driver as well, especially in the modern, since the Industrial Revolution started. Higher product quality and productivity is connected, of course, there. Manual work to more fully automatic work were also drivers. So we needed more machinery that were assembled in a way that they could be more precise, besides doing human work. And of course, here we see an example. In the middle of the 18th century, machines was often made of wood. Later on, they became made of steel, so you can have them more tightly connected with high precision. And one of the first examples was John Wilkinson's cylinder boring machine, 1795, that could drill steam engines cylinders to very high, for that time, accuracy. Of course, this didn't happen overnight. It was a gradual evolvement over the subject. So it started quite earlier with some ideas that we see here, to going from parts made of wood to steel parts, combining different mechanisms together to create quite complex mechanisms, as we see here, to Chambers' Encyclopedia here, where you combine the different mechanical systems into quite complex mechanical machinery to produce parts. But usually, the birth of the modern precision engineering started with this cylinder boring machine by John Wilkinson. So he actually enabled, through his system, so that John Watt could make steam engines more efficient, so you don't need so much fuel in coal and so on. So tighter cylinders made that you have less leak stream going out from the steam engine, and by that the efficiency increased a lot. So usually we say that John Wilkinson was the inventor of precision boring systems. And then of course after him there come other persons as well that refined even his designs. And one of them was Henry Maudslay, as we see here. We say that he made the first machine tool, a machine that can make other machines, basically. So he replaced some parts here, so he had a quite stable stock, and he replaced, for instance, the ball screw that made the feeding mechanism to steel-made ones. And that created a lot of possibilities to have a higher precision, as we see here. If we take this a step further now, you can also think, okay, how should we design our mechanical system to be precise? We cannot only design them in some cases towards a certain product. We need also to have some basic understanding and basic principles. And a researcher named Pat McKeown, he came up with 11 principles how to design precision systems. And those 11 principles is basically telling from the structure, how to design a mechanical structure, to how to measure things in that structure. As an example, we see here, this is a small precision machine that manufactures high accurate parts for instance, mirrors in different applications in optics and so on. To give you an understanding, the tool size here could be around 1 millimeter in diameter. So it's quite small things in this case here. So things you need to think about when you design: thermal effects, for instance, how are your gradients, how is your, for instance, control system with the electric motor heating up the machine or the machinery. That needs to be taken into consideration. How you do error compensation, error budgeting is also important, other topics to compensate for deviations. But first of all, you need to have a quite good design on the mechanics and the control system and so on before you start to do compensation. Today we see the drivers, and this is from my point of view here, the drivers for doing precision manufacturing with this thing is maybe not so much on the interchangeability of components. That was the early needs that we saw. Today we see reducing of energy consumption and rework is very important in a sustainable global environment we are living in today. We also need to have greater miniaturization, for instance in silicon wafers manufacturing of IC circuits and so on. And one thing that will always be there is this improved quality and quality control of components. Because as we see in the future, components will be made much more accurate, and so we can reuse them in multiple life cycles, for instance. In that sense, we need to design and manufacture our components in a precise way. So how do we manufacture components, and how do we design and produce things? So basically, beside us humans, we have two systems there. One of them is robotic arm manipulators to assemble things, to press fit and so on. And the other thing is machine tools. So machine tools is typically a machinery that manufacture parts that you can later on assemble in the process, in the manufacturing process. So usually these two type of mechanism or machinery are involved in all type of production in the value chain. And typical components that we manufacture today are for the automotive industry. In this case, we see a cylinder block for a V8 engine. This is a die for a toy, for Lego, typically. Or this is a part of an aeroplane, as we see here as well, a big side view here. What is interesting to see, the trend is ongoing now, is that the precision of components are getting better and better all the time. The accuracy level is increasing. And if we compare a component like this one with in a heavy-duty truck, for instance, we are almost on the same level of accuracy demands, around 5 micron in this case. There is, of course, other extreme examples that even tighter tolerances. So regardless what kind of component you manufacture today, you need to think about how precise are your system and how is it designed to deal with, for instance, thermal issues and so on. Even for big parts like this, okay, maybe we are not on this level of 5 micrometer accuracy, but in comparison with the size of the components, a millimeter might be high precision in this kind of application. So there you also need this type of thinking. So to get your figure of how big or how large is 5 micrometer is like you take a hair and you cut it around 20 times, and then you take one of them, and still you are not on the level here. So a hair is around 80 to 100 microns. That's the level of accuracy you demand on your precision machinery today. And this is under high load, so you can have forces acting in a system like that up to 2, 3, 4, 5 kilonewtons and even more, much more than that. And still the machine needs to be able to produce. Other application areas is large telescopes, where we see as an example here, the ASO, European Southern Observatory, where you use precision metrology to identify the position between the large meter and the smaller meter there, the reflector there. And by that, you can use that to estimate, doing modeling, and identify if you need to do any compensation. So it's not only the manufacturing part, also the metrology. They are quite tightly, or they are very tightly connected in this area. So influencing factor on accuracy in any kind of machinery that are made of mechanical parts, basically, or compensations and so on, is, we usually say it is 4 physical attributes. It's the geometric part, accuracy, including position and kinematic accuracy, static accuracy, thermal accuracy, and dynamic accuracy. So that are the factors that we need to take in consideration when we look at precision and precision design and so on. Of course, you can refine it even more through this diagram as we hear, the effect on, let's say, a machine tool. We have a lot of factors affecting it, and in some cases it's quite difficult to deal with all of them in the same time, so you need to have a systematic approach to understand. And one way to get the systematic approach is to measure. That's why metrology and precision are very tightly connected. One example is a device that we designed here at KTH some years ago. It's called loaded double ball bar. It's basically a measurement tool where you can measure the quasi-static behavior on a machine, in this case. And to give an example, if we measure, it's a cylindrical measurement, so we measure in a circle with this tool. A perfect machine without no distortions give this type of circle. But what this tool can do, this instrument, is that it can add a load to the measurement. And that's usually it's not a trivial thing to do, because you need to understand what deformation you get. Is it in the tool, in the machine, and so on. But what we see here, when we increase the load with around 100 Newton, we see that the machine deviates from its nominal part. So that shows why it's important to measure mechanical system or machinery under loaded condition as well, not only unloaded. With this one, it's like a fingerprint. We understand more about our machine and we can use it for compensation. As an example here, we measured quite many different machines, and we saw actually that this fingerprint, by calculating the stiffness by this measurement, we see that they are quite different. So it's like a fingerprint if you compare us humans. And that's a typical application where we use metrology to understand more how our machinery is behaving. Here's another example. Sensor-based metrology is coming more and more. As an example here, I brought a small bag. If you have time afterward the presentation, you can come look here. So this is including an accelerometer, and you can clamp it on your mechanical system and make some special movements, as you saw in the movie here. And by this approach, we can measure actually down to a couple of micron in accuracy, for instance, in straightness of an axis movement. So this is also a trend that we see today now with precision metrology, that we're using sensors to identify the behavior of the machine and use that information for data analytics and so on. Precision is not only in this kind of application, but we also see it, for instance, as an example in the ongoing work on the revision of the SI unit system. As you know, many people have stated that it's important to be able to quantify things, to have a meter to relate it to something, and to measure it in different way. And we have seen example in history where we are using the foot as length of unit, and there is a local villages that have their own ways. So this is an example of how the map of Europe was divided in different kingdoms and so on. And all of them had quite different ways to measure things, and we need a standard way. And that's why the SI system was finally agreed on, and that kind of helped us to understand more and compare things, to have this interchangeability we have to things and compare it. And to see evolution of the length measurement, we started from meter convention, 17 member states started to work on this, and 1983 we redefine it. Instead of having this meter in Paris, we are actually looking at how how far light comes in a certain time span. And by that we could have a meter defined on a universal constant rather than a physical object. And we also see here in this map that comparing the measurement of speed in light and the length measurement are almost on the same level of accuracy today when we do measurement and things. So the ongoing work now is regarding the mass. The mass, as you know, is until now it's a kilogram prototype in Paris. What has been identified some years ago is that mass is not stable, it changes mass. And actually it's per definition the kilogram, and we as humans cannot have something that changes. We need to have a definition that are stable. So ongoing work now is to not be dependent on the mass, the kilogram mass in Paris, but to have it connected to a physical constant instead. Actually, two independent methods have been developed or under development. One of them is the Kibble-Watt balance, and the other one is the Avogadro project. And both of them are actually enabled through precision engineering and metrology. So for instance, the Watt balance in the left side here uses balance to compensate gravity forces and electromagnetic forces. And the macroscopic single crystal, as we see here, is for the calibration of the Planck constant, number of masses in atom and so on. And to give you an example here, to get this sphere, as we saw that's the most roundest object in the world, we need to manufacture it through precision principles and precision manufacturing, and then measure it through metrology. So to design a component like that and to manufacture that we see here is a lot of quite delicate steps to do it, to be able to do it. So as we see, we start from a quite rough component there, and then we do some processes on it, then we measure what is the deviations, then we do some other processes on it, and so on and so on. But the whole process is through this precision thinking where we need to have a systematic way to work. And then at the end we are having a lot of quite advanced features in order to do this establishment of the new mass standard, not against the kilogram, but against a universal constant instead. So, summary. Precision engineering and metrology will become more and more important. For instance, lower energy consumption in trucks, cars, all type of systems, aeroplanes as well. The high quality demands will increase. We need to have high accuracy parts that are interchangeable and last long. And we also need to have dependable systems that we know the behavior of. Or if we don't know the behavior, we need to adapt to the new behavior. That's important. And there we see that the precision philosophy is a crucial part of that. We also see trends, integration of metrological instruments and sensors and machinery. That in combination by using digital models, would be this point here, is also important. So using the measurement as a calibrator or a tuner for the model, and then you're using the digital model to do the estimating of a behavior. That's also a trend we see today. Fusing of multiple sensor metrology data is also a very important area, connected to edge computing and so on, where we want to distribute it and to fuse multiple data sources together to get a better understanding how the different parts are allocated. We also see from practical point of view this electrification that we hear a lot of people in the automotive talking about. I have attended meetings where people are saying that going from, let's say, conventional drivetrain in a car to electrified drivetrain will change to 70% some components in such drivetrain. For instance, cylindric rotor symmetric components will probably be much less in electrified drivetrains. That will have an effect on the precision engineering industry as well, for manufacturing and so on. And repeatable designs is also something a lot of people are working on. If the system is repeatable, then you can do compensation on it. But if it's not repeatable, it's quite difficult. So therefore, a lot of systems are designed today with repeatable features and so on. So that's also important to state here. And then, of course, the SI unit, most likely, or to high likelihood, 20th of May, the new system will be launched. And look for that in the news, because that will be a very interesting thing to look deeper into later on. Finally, so how did Michelangelo do it? So it has quite challenging features, We said it's 5 meters tall, small features, 1 to 1.5 millimeter. Deliberately bumpy surfaces, because that makes small shades, so it looks more living, the tissues and so on. It's manufactured tools. Oh, now you don't see it here. Manufacturing different tools to be able to do all these small features. And the surfaces look something like this one. So what do you say, guys? So of course, he combined at that time design with art. So he had an idea how to design it, of course. He had manufacturing processes. So he designed his own tools and manufactured his own tools to make these bumpy surfaces and so on. And he used, in his sense, the metrology tool that we have is so crucial for precision today. So by looking at things, he measured, maybe sometimes only with his eye, sometimes with some tools, and then he iterated this slowly. And was able through that process design a fantastic piece of art like we see here today, that was made of a very difficult to work material, marble and so on. And one single mistake would ruin the whole, but he was able to do it. So the same principles, or not the same, but of course they are developed more today, but I see that also that the principles of precision was used there, but in another different context than we are doing today. Okay, thank you so much. That was all for today.
Great. So does anyone have any questions? Yep.
I wonder how you have precision engineering in other materials, like you talked about ceramic and metal. What about polymer materials, which are a little more unstable? How do you handle precision engineering in that?
Ooh, that's a very tricky question. I don't have so much experience from that, but I guess it's I mean, the principles would also be applied there, but then I guess it's more the details, what tools you are using. For instance, if you want to shape a component, or if you want to made of those kind of material, and how you would have the application with it. But I guess the system around it. For instance, when you want to design a system or a component or manufacture a component, you also need to think about the environment around it, how you make stable conditions for that type of applications. And for those things, we see the same principles will be used there.
I believe so too. It's important to point it out. It's a difference.
Yeah, because the important thing also is the domain knowledge, that you need to have multiple, knowledge from different sources in order to be successful in this. Not only looking, for instance, on computer science or electronics or whatever, or mechanical, but you need to combine them together here.
Any more questions? No one? Well, thank you very much, Andreas.
Thank you.
Here's a little present
Oi.
from KTH Library.
Thank.
And I hope to see you all here again in 2 weeks' time, when Wouter Metzler van der Wingart will talk about nanoengineering, May 8th. Thank you very much.
Thank you.